All right, guys. So I wanted to talk a little bit about concentration, right, and kind of bring that into a discussion real quick about electrolytes. Okay. So concentration, when we're discussing this in terms of a solution, right, this is basically a measure of how many solute particles are dissolved in a given volume of solvent, right, of water. Okay, so for example here, I want to draw some particle diagrams, what it would look like if I mixed 1 gram of copper sulfate. Okay, so for 1 gram, I'm going to draw in 5 particles. Okay, so I'm mixing 1 gram with 10, 20, 30, and 50 mils of water. Okay, so 1 gram goes into each one, and I'm changing the volume of the water that I'm dissolving it in. Okay, so for our first one, I got my 1, 2, 3, 4, 5 particles. Okay, 20 mils of water. I still have 5 particles. 2, 3, 4, 5. 30 mils, I still have 2, 3, 4, 5 particles. And 50 mils, I still have 1, 2, 3, 4, 5 particles. Okay, so now we want to stop and think about this. All right, what's this mean? Okay, so concentration, right, this one that's 10 mils, it has the same amount of solute, but it's in a smaller space. It's compacted closer together. Okay, so this one here is more concentrated, right? Because those solute particles, they're occupying a small volume, right? Only 10 mils of water. Okay, the same number of solute particles are going to be dissolved in 50 mils of water over here. This one is going to be less concentrated. Okay, so it's the same number of particles, but now they're more spread apart. Right? They got more room in there. Okay, so concentration is all about how close are those particles to each other. Okay, so I want you to think about this for a second. Right? How might we see this? Like, how might this be different in, the macroscopic scale? So, like, say you have a beaker of water, you put a drop of food coloring in, right, and you slowly add more and more and more water, right, going from 10 mils up to 50 mils. What's going to happen? Right, think about that for a sec. All right, so if you've thought about this, you can try it out. Get some food coloring, just put a drop in there, like a glass of water, and slowly, start filling up that glass of water more and more and more, right? And we should see that the color starts to fade. Right? It might be like a really dark, vibrant color, right? So you're using blue, so it's like a really dark blue. But then as you add more and more solvent, right, more water to that, then that blue color, right, it starts to lighten up, it starts to fade, right, and becomes less and less blue. And eventually, if you started at like a glass of water and you had enough water to, say, fill up a swimming pool, right, that might be so much water that the blue color more or less disappears. Like, all those particles are still in there, it's just now they're so far spread apart that we can't really tell that that color's in there. Okay, so concentration is all about how closely compacted together those solute particles are. Okay, and I should say here also, another way of saying this, instead of calling this 50 mil one less concentrated, we could also call this more dilute. All right, so when we add water or add solvent to a solution, it's called diluting, right, or dilution. Okay. The other thing I want to take a look at here is electrolytes. Okay, electrolytes, essentially, these are just solutions that will conduct electricity. Right? Some solutions conduct electricity, but not all solutions conduct electricity. Okay? In order for something to conduct electricity, you have to be able to carry that charge around. Okay, so ionic compounds, when they dissolve, okay, they are going to be able to conduct electricity because when they dissolve, they have ions, right? They break up into Na plus, Cl minus, right? They have those charges, right? So those ions carry the charge. Covalent compounds, however, are going to be poor conductors because they do not break up into those ions, right? They stay together. Right? Think back to when we were discussing that dissociation. Right? We said that ions like NaCl, right, or in this case down here, calcium chloride. Okay, when it dissolves, right, it's going to break up into its component ions. So I got calcium with a +2 charge. I'm going to put the AQ to show it's dissolved, and it breaks up into chloride. Cl minus, again, put the AQ to show it dissolves. And I've got 2 of those chlorides, so I'm going to put a 2 there. So here I've got ions. Right? Compare that to something like, this is formaldehyde here. Okay, formaldehyde, this is covalent. Okay, so it's not going to break up. It's going to stay CH2O. Right? And I'm just going to put that AQ here. Okay, so this one, there's no ions, there's no charges, there's nothing to carry that current within the solution. All right, let's take a look at an example here. Okay, so I want to complete those solvation reactions. Okay, so first off, I'm going to look at Ca3PO42, right? Calcium phosphate. Okay, this one is ionic, right? I know it's ionic because I got a metal and I got nonmetals. I have a polyatomic ion, that PO4, right? We should be able to recognize that. PO4 is polyatomic. Okay, so when this guy breaks up, I'm going to break up into Ca2+. Right, let me put the AQ in there. And then phosphates, it's going to stay PO4. Give that AQ. And phosphate, you can look it up on the back of the periodic table, has a -3 charge. Okay, I've got 3 calciums and 2 phosphates. Okay, and then looking at the other one, I got C2H5OH. This is ethanol. This is covalent. All right, and again, I know that because these are all non-metals. There's no metals in here, no charges, no polyatomics. Okay, so this is covalent. So this guy is going to stay together. C2H5OH. I'm going to put that AQ afterwards. Okay, but there's no charges here. Right? So then looking at this, right, which bulb would we expect to light up? Right? The one that has the ions is going to have charges that will carry electricity, so I would expect this one here to light up, right, because it has the ions. Okay. Lastly, why does NaCl aqueous conduct, right, but NaCl solid does not? Right. So if we think about this, NaCl aqueous, that means it's going to be broken up into Na plus and Cl minus. So it's going to have those ions with those charges that'll be able to carry the electricity through, and it will make the light bulb light up. NaCl solid, that's going to be all stuck together in that lattice that we were talking about before. Right? So those ions are not able to move around. They can't carry the charge. So a solid is not going to be able to conduct.